Hello students, in this video we'll discuss elementary operations on matrices. Let's recall a matrix is an array of numbers. For us, it can either be real or complex. Okay? So it's an array of numbers, and how is this array configured? We say that A is m by n if there are m rows and n columns. Okay, so we always say rows first, then we go to columns. Okay, so for example, simple example, I can look at this matrix over here: 1, 1, 2, 3, 4, 3, 2, 1, 6, 1, 5, 8. Right, so over here we have what? We have 4 rows, so this is a 4 by 3 matrix. Again, those are our rows, and those are our columns. And in this way, we can specify entries of the matrix too. So for example, I can say that this number over here, 5, that 5 is the what? 5 is it's the third row, third column entry over here. Likewise, we can say that this 1 is the fourth row, second column entry. Okay? So that gives us a way of specifying rows and columns and entry numbers in the matrix. And now I want to do some algebra of these matrices. So it's the algebra of these matrices. So we're going to do 3 operations. So the first operation we're going to talk about is addition. So if A and B are both m by n matrices, so they have to have the same dimension, then define A plus B to be an m by n matrix with entries A, I, J plus B, I, J. Where what are these A, I, J, and B, I, J's? These things are going to be, that's the I, J entry of A, and this is the I, J entry of B. Okay? So you add the corresponding entries as you would expect to do. Similarly, for scaling, so if A is m by n, then in K, A is m by n, and here this K is just a real number, so K is a real number. And the entries are what? The entries are just K, Aij. You multiply the corresponding entry by Aij, okay? So let's do an example. This is actually really simple to do. So for example, if I have this matrix A, which is 1, 2, 3, 4, 5, 6, and B is the matrix what? It'll be a 2, -1, -1, 3, -1, +2. So both these matrices are 3 by 2 matrices, and so I can add them together, right? So I can say A plus B is trivially equal to what? We'll do this quickly. It's going to be a 3, then a 5, then a 2, then a 3, then a 4, then an 8. And we can see I just add the corresponding entries together. So for example, to find that 3 over there, I just did the 1 plus the 1. So the 1, 1 entries add together give me a 3. Then for example, the 2 entries add together give me a 3 also. The 3, 1 entries add to give me a 4, etc. So I'm adding component-wise. So we're adding the components of the matrix together, the components of each of the matrices, corresponding matrices together to get the sum of the matrices. Very simple to do. Likewise, I could say, what would 6 times A be? 6 times A, for a real number, would be what? It would be A, let's do it carefully. So we're going to have 6 times 1, that's going to be a 6. 6 times 2, that's going to be a 12. 6 times 3, that's going to be an 18. 6 times 4, that's 24. 6 times 5, that's 30. And 6 times 6, that's 36. In other words, we're multiplying everything by that scaling parameter. So that's how we do addition and scaling of matrices. Now, those are relatively straightforward. They give me a nice sort of a group structure for this addition between matrices and scaling. It gives me this vector space structure. But now, of course, one of the more interesting ones is this idea of transpose, right? So if I have a matrix A, which is an m by n matrix, then I can define a transpose to be an n by m matrix by interchanging the rows and columns, by interchanging rows and columns. Okay. And so, of course, transposing is also relatively straightforward to do. So, for example, if I was to do 1, 2, 3, 4, 5, 6, this is a 2 by 3 matrix over here. And if I was to transpose this matrix, so this is my matrix A, this will turn into A transpose. A transpose is going to be a 3 by 2 matrix. So it's going to be a 1, 3, 5, and then a 2, 4, 6. And we can notice, of course, that all I've done here is I've simply taken the first row of my matrix A and I've turned it into the first column of the matrix A transpose. And I've taken the second row over here of A and I've flipped it, I've changed by 90 degrees into the second column of this matrix over here. Now the cool thing about transpose, there's a couple how does transpose work with addition and scaling? Transpose works with addition and scaling according to the following results. So we have a very, very simple theorem to prove. So here's our theorem. Here's the first part of our theorem. The first part of our theorem is that if I do A transpose, and then I transpose again, so let's think about how we would prove something like this. So it's very simple to do. So in other words, if I take the transpose of A, that's shifting the rows and columns. If I transpose that again, I shift the rows and columns, and that restores the original matrix. So it's an involution, so that you get back to A. So if you transpose twice, you get back to the original matrix. That's easy to see. The second thing we have about transpose is that it works well over addition. So A plus B transpose is equal to A transpose plus B transpose, so it works over addition. And then the third thing we have is that it works over scaling like this. If I do K times A transpose, that's just K times A transpose. Now, of course, the transpose will come up a lot in further studies when we start talking about symmetric matrices and special properties that symmetric matrices have, or normal matrices. Those are matrices that commute with their transpose. And so there's lots of very special properties that correspond to transposing things, in particular for square matrices, and we'll see those in further videos. Thank you very much.